Look up. Tonight a horned visitor skirts our sun, a comet so strange it's been nicknamed the Devil Comet. But this is not just spectacle. Recent outbursts have revealed a secret that could rewrite how Earth got its water. In 12 minutes we will follow the Devil Comet from its icy heart to its violent eruptions, and trace a trail back to Earth's oceans. We will unpack real data, spectroscopy, isotope fingerprints, and comet cryovolcanism, and reach a surprising verdict. So hold your breath, because the Devil Comet might be a relative, a messenger, even a midwife to life on Earth. We begin with a puzzle. How did a hot, molten young Earth ever become drenched with oceans? Clues hide in isotopes. Tiny differences in hydrogen that act like cosmic fingerprints. Comets carry those fingerprints. And Pons-Brooks has shown us something unexpected. Water that smells suspiciously like our oceans. We'll meet the suspects, volcanoes, asteroids, comets, and follow the forensic trail to a new verdict. Start the countdown, our first stop, the blue world we call home, and why its water is the deepest riddle of all. From space, Earth is a blue oasis, over 70% water, a shining exception in a dry solar neighborhood. Water is the stage upon which life plays. Oceans, rain, ice, groundwater, and even our bodies are largely water. All Earth's water would fit into a sphere roughly 860 miles across, a colossal volume that demands an origin story. But Earth formed close to a hot young sun, conditions too warm for ice. The rock that formed Earth should have been dry, so either water came from inside, volcanic outgassing, or it was imported later by extraterrestrial bodies. This isn't academic. It's the question of how Earth became habitable and why life appeared here and not on many other worlds. To solve it, we read ancient clues, isotopes and chemistry trapped in meteorites, asteroids, and comets. Next we assemble the lineup. Deep Earth volcanoes, rocky asteroids, and icy comets, each with a different fingerprint. We begin with the world that birthed us, the molten Hadean Earth, to see why external delivery was necessary. Brace for a violent ancient sky, the scenes that made delivery possible in the first place. 4.5 billion years ago, the solar system was violent, a disk of gas and dust grinding into planets by collision. Gravity shoved dust into planetesimals, planets formed in a chaotic mosh pit of impacts. Earth grew by violence. Early Earth was molten, a magma ocean under a toxic sky, too hot to hold ice or oceans on the surface. A titanic strike with a Mars-sized Theia may have formed the Moon, another vivid reminder of the planet's violent youth. Later, the late heavy bombardment flung countless objects at Earth. Asteroids and comets rained down in astronomical numbers. Any primordial ice in local building blocks would have vaporized from heat or been stripped away by solar winds. Earth needed deliveries. Only after the planet cooled and gravity stabilized could it begin to hold on to volatiles, opening a window for imports to stick. So what could perform that import duty? We return home, volcanoes, or the deliverers from space. In the next scene, we assemble the suspects, weigh the evidence, and ask which could explain Earth's oceans. Prepare for chemistry and isotope fights, the fingerprints that decide guilt or innocence. To crack the case, we assemble 3 suspects: deep Earth volcanism, asteroid hits, and icy comets from the outer reaches. Volcanic outgassing can release water trapped in minerals. Steam from eruptions could condense into primitive oceans. But isotope studies of mantle-derived water don't fully match ocean water. Volcanoes help, but they don't close the case alone. Asteroids, especially carbonaceous ones, carry hydrated minerals. Their isotopes often closely match seawater. Analyses of meteorites returned to Earth show DH ratios consistent with seawater, a major clue in favor of asteroids. Comets were long considered prime suspects. They are vast reservoirs of water ice. But early comet data complicated the story. Measurements of many Oort cloud comets showed heavy water, too much deuterium compared to Earth's oceans, weakening the comet theory. Recent work shows diversity. Kuiper belt comets can have lower DH. That reopens the door. Enter Pons-Brooks. To evaluate Pons-Brooks, we must look inside. Cryovolcanism, jets, and composition. The anatomy of a comet. Next, why Pons-Brooks erupts like a beast, and how its plumes reveal hidden chemistry and isotopes. 12P Pons-Brooks is a Halley-type comet with a horned coma and explosive cryovolcanic outbursts that light up our skies. Its nucleus spans tens of kilometers, comparable to a mountain or even a small city, carrying enormous reservoirs of ices. Inside, water ice, CO2, Colorado, methane, ammonia, dust, rocky chunks, and complex organic molecules. A frozen chemical kit. Cryovolcanoes erupt icy slurries and gas, sunlight warms subsurface volatiles, pressure builds, and explosive jets punch through the crust. Asymmetric jets carve a horned coma, the Devil Comet's signature, revealing where interior materials escape to space. Each outburst ejects pristine interior material, a remote sampling of 4.5 billion-year-old ice and organics. Telescopes capture that light and feed it to spectrometers, a barcode of molecular fingerprints that tell us composition and isotopes. In 2023, Pons-Brooks erupted spectacularly, brightening by orders of magnitude and giving astronomers a bounty of fresh data. That data held the critical clue, a deuterium fingerprint that forced scientists to rethink comets' role in delivering water. Come closer, a single neutron in hydrogen, deuterium, can settle this case. The numbers matter. Hydrogen has a heavier sibling, deuterium, and the ratio DH in water acts like a cosmic fingerprint. Cold outer regions favor higher DH. Warmer inner regions produce lower DH, so formation location leaves a mark. Oort cloud comet measurements showed DH 2 to 3 times Earth's, a mismatch that casts doubt on comets as ocean donors. Carbonaceous asteroids sampled via meteorites and missions yielded DH very close to seawater, a strong asteroid case. But newer observations, especially of Kuiper belt comets like Pons-Brooks, showed much lower DH than Oort comets. Pons-Brooks' outburst allowed high-quality spectra. The DH measured is close to Earth's oceans, unexpectedly familiar. This implies comets are not monolithic. Some formed in regions that produce Earth-like water, reviving their role as contributors. The simplest conclusion, Earth's oceans are a cocktail, mostly asteroid water, with a significant contribution from certain comets. But how did those comets and asteroids reach Earth? The answer lies in the dramatic era of bombardment. Next, planetary migration, giant planet gravity, and how the solar system flung icy worlds inward. Between about 4.1 and 3.8 billion years ago, the inner solar system endured a storm of impacts, the Late Heavy Bombardment. Giant planets migrated into new orbits, their gravity scattered asteroids and flung comets inward like cosmic cannonballs. The sky would have been filled with streaking meteors, exploding fireballs and comet showers, a violent delivery system. Each impact could vaporize material and release water and organics into the atmosphere, allowing condensation and ocean formation. Modeling shows a mixed contribution from asteroids and certain comets, best reproduces Earth's current isotopic fingerprint. Beyond water, comets delivered complex organic molecules, the raw materials that may have sparked prebiotic chemistry. It was violent, yes, but that violence created the very conditions for oceans and the chemistry of life to emerge. So the stage was set. Diverse cometary water, asteroid deliveries, and planetary dynamics combined to fill Earth's basins. Today we test these ideas with telescopes and daring missions, looking at comets as living relics of that era. Next, how cutting-edge instruments read comet outbursts and why sample returns are the holy grail. We now have new eyes, JWST large ground telescopes and spacecraft that can sample comets up close. Infrared spectroscopy reveals water, organics, and isotope ratios from afar, reading plumes as if in a lab. Rosetta taught us comets are complex, active worlds, not simple dirty snowballs, and sparked the next generation of missions. Missions like the proposed Caesar would return pristine comet samples, allowing lab analysis beyond spacecraft limits. These missions are expensive and take decades to design, but their payoff, definitive isotopes and organics, is immense. Pons-Brooks shows what to look for: eruptive comets with Earth-like DH, prime targets for future sample return missions. Back on Earth, mass spectrometers, synchrotrons, and microscopes can tease out isotopes and organics at sub-ppm precision. These missions inspire the public, amateur astronomers spotting outbursts, crowds watching telescopes, a global scientific effort. Armed with telescopes, spectra, and future samples, we can finally weigh the evidence and offer a verdict on our water origins. Now, the final act. What does the total evidence say about the Devil Comet and the birth of oceans? So, did the Devil Comet bring Earth's water? The answer? Partly yes, and wonderfully complex. Asteroids likely supplied the bulk of water, but comets like Pons-Brooks contributed a significant fraction and crucial organics. Pons-Brooks demonstrates comet diversity and provides a smoking gun, Earth-like DH in a cometary plume. Beyond water, comets may have delivered organics that seeded prebiotic chemistry, a nudge toward life's first steps. Uncertainties remain: exact contributions, timing, and how organics survived impacts, which is why missions and samples matter. Remember, the water in your glass may have once been ice in a comet, forged in the outer cold and delivered by cosmic violence. As JWST and future sample return missions advance, we'll refine the numbers, and maybe find more devil comets with ocean-like water. This is not just geology or astronomy, it's our origin story. Comets link us to the wider cosmic family. If this fascinated you, subscribe for more cosmic mysteries. Like, share, and comment. What would you ask a comet if you could? Keep looking up. The answers are written in light, in spectra, in rocks, and in the silent paths of comets like Pons-Brooks.